Hello everyone, good evening. So today we are going to start with the important topic in mechanics, which is work, energy and power. So I think we would have already talked about this point, the Newton's laws of motion and this work, energy, power, right? These two are considered as the core mechanics topics. Like even when we go to the other chapters, we'll see that the principles of core mechanics, right, they will get used. Like even when we go to chapters like electrostatics or magnetism, or even when we go to say for example the modern physics chapters, also we will be using these core mechanics principles. Okay, so we'll start with the introduction to work. Okay, so broadly in this topic, right, what we are going to cover is we'll try to understand what is this work and how we'll be able to measure the work. Okay, so that is what we'll try to cover in today's session mostly. Then we will classify the forces, because work will be done by the forces, and we'll try to classify the forces based on certain consideration as conservative forces and then non-conservative forces. Then we look at the work energy theorem and applications of the work energy theorem. Then we have the idea or the study of collision and explosions. Okay, so this is what broadly we have to cover in the entire chapter of work, energy and power. Okay, so first we'll begin the discussion with what is work. Okay, see, generally we do a lot of work, right? Like say when you're writing something on the paper or when you are taking notes, that is also, we'll consider it as a work. Like when somebody is pulling an object, or somebody is trying to hold an object, or maybe you are washing the clothes, or I mean anything, washing the utensils. So a lot of things that we do in general, right, we'll say we are doing work. But the point is when it comes to the concept of work in physics, we have a certain way of defining it. So generally, even if you are writing something on the paper, you are actually doing some work, right? But that is the common notion of work. But when it comes to physics, we have a method of defining what is a work. Okay, so in the physics context, right, work is said to be done when the applied force on the object or the body displaces the body in the direction of the force. So how do we define the work in the context of physics? When we are applying a force on a body, say for example there is an object. Okay, we are applying a force on the object. Okay, so force may be in any direction. Let's say there is a force in this direction. If there is a displacement of the body in the direction of the force, if there is a displacement of the body in the direction of the force, say for example this is the direction of the force, right? So the arrow here represents what? The direction of the force. So there should be some displacement in the direction of the force. Only then work is said to be done. If there is no displacement in the direction of the force, then work is not to be considered in the context of physics. How we'll actually go and find out the work done by a force, we'll discuss about it. But generally when we want to estimate the work done by the forces, right, we'll try to divide the forces into two categories. One is the constant force, and second is a variable force. The basic approach will be similar, but there will be some small differences, we'll see. So we'll start with how do we find out the work done by a constant force. Okay, say for example if there is an object, on this object we are trying to apply a force. Because of this the object, this is a constant force. Okay, so we are considering a force to be constant, means it will be having a constant magnitude as well as direction. So both will be constant for the force. Okay, let us say the body is getting a displacement. Now displacement need not be, displacement is also vector, right? It need not be in the direction of the force, it may be in some other direction. Let us say the angle between them is what? Theta. Theta is what? The angle between the force vector and the displacement vector. Okay, so let us see how do we define the work done by the constant force. So work done by the constant force, right, is measured as, what is the thing that we talked about? The work is said to be done when there is a displacement in the direction of the force. So when you apply a force, we are looking at what is the displacement of the body in the direction of the force, correct? So look at it. So S bar is a vector. Let us say the magnitude is what? S. Force magnitude, let us say, is what? F. Now look at it. The component of displacement vector along the direction of force. What is the component of the displacement vector along the direction of the force? Look at it. What is the angle between the two directions? Theta, right? So what will be the component of the displacement? S cos theta. This is something that we already learned in the vectors. So displacement is like this. It is making an angle theta with the direction of the force. Means the component of the displacement in the direction of the force is what? S cos theta. So work is measured as what? The force magnitude multiplied by what is the component of the displacement along the direction of the force? It is what? S cos theta. So what is it? It will be F into S into cos theta. So the work done by the constant force, right, for a given displacement with theta as the angle between the force vector direction and the displacement vector direction, right? What is the work done? It is what? Fs cos theta. Now the same thing, right, we will also try to understand this in terms of a notation that we are already comfortable with. Let us say, for example, in the same, we have a constant force, and the constant force is giving a displacement S for the object. So this is the force, we are applying a force in a direction, and the displacement is here. What is the direction of the displacement we are representing? Horizontal. Okay, now what is the work done by this constant force? Already we have talked about it. What is the work done? It is measured as what? F into S into cos theta, correct? Now if you just rearrange them, right, we can also rearrange it like this. How? F cos theta into S means either we define the work as what? The force multiplied by component of the displacement in the direction of the force, or the component of the force in the direction of the displacement multiplied by the displacement value. Because remember, so if we have a dot product, what is the dot product of two vectors? Here the two vectors that we're talking about are what? Force vector and the displacement, right? What is the dot product? It is what? F dot S will be what? F into S into cos theta. Remember, we talked about the way we will define the dot product. So if you have dot product of two vectors, right, what is it? A B cos theta. We can write it like what? A into B cos theta. We can also write it like what? A cos theta into B, isn't it? So which means what? We can define the work as the force multiplied by component of the displacement in the direction of the force, or component of the force in the direction of the displacement F cos theta into displacement value. Either way we are going to get the same value for work. And how we can look at this relation? Because force and displacement are vectors, right? We can look at it as the dot product between the force vector and the displacement vector. So whenever we want to measure the work done by a constant force, right, what will be the formula for measuring the work? It is nothing but the dot product between the force vector and the displacement vector. That's it. So if we are able to get the dot product, we will be able to find out what is the work done by the particular force. Okay, so this is how simple it is to find the work done by a constant force. Now when we talk about the features of the work done, features of the work done means we are trying to understand what will be the characteristics of the work done. See, when you look at dot product of two vectors, remember in the discussion about the dot products we have learnt about it. dot product value will be positive when the angle between the two vectors is acute angle. So look at this here, we're talking about the dot product between what? Force and displacement, right? If the angle between the two is an acute angle, so angle 0 to 90 means what? This is the acute angle, right? So in this case, what will be the work done? It will be positive. Okay. And if the angle between the two vectors is obtuse angle, means more than 90, then in that case, what will be the dot product? Because remember what we will get? In this case, we will get Fs cos theta, right? Cos theta in the 90 to 180 means what? It is the second quadrant. Cos theta will be negative. So for the angle between force and displacement vectors, if it is an obtuse angle, means the work we are going to get will be negative. So work can be positive, work can also be negative. It is not like always work has to be positive. Work can be positive, work can be negative. Not only that, we will also have situations where the work done can be zero. Let us see what are all the cases where the work done can be zero. So look at this one. Think about a person who is holding some, like in this case, what is this person doing? He is holding some weight on top of his head and he is walking. The person is actually walking, which means what? For this object that he is holding on top of his head, he is applying a force. He is applying a force on that object, right? That is how he is able to balance the weight of the object. The force applied is what? Upwards. But what is the displacement he is giving for this object? He is moving on the horizontal ground, means displacement is what? Horizontal. So what is the angle between the two? 90. Remember, if two vectors are perpendicular, then what will be the dot product? In this case, F dot S will be what? 0. So here you have a force, there is a displacement, but the problem is what? I mean, it is not a problem, but the condition is what? Here we have the angle between the two 90. So the dot product becomes what? 0. So when you have the force and displacement perpendicular, then the way we will measure work in physics, right? It will be taken as what? 0. Not only that, like say for example, we have a person who is trying to apply a force on a heavy mass. Like in this case, right? This boy is trying to apply a force on the heavy mass. This heavy mass is not moving. Obviously very difficult to move the heavy masses, right? So he is applying a force, but it is not moving. Then in this case, right, he is applying force. But for us, when we want to look at what is the work done by him, right? What will be the work done? Because there is no displacement. Since there is no displacement, right, the work will be what? 0. Work will be what? 0. And if say for example, in some cases, there is no force at all acting on the body. In a particular case, there is no force at all. Means F is 0. On a particular object, we don't have any force acting. Then in that case also work will be what? 0. So we have work. It can be positive, it can be negative, it can be 0 also. So what are the conditions where the work can be 0? You can have a 0 work when the force and the displacement are in perpendicular directions. You can have 0 work when we are applying a force but there is no displacement. And again, if there is no force at all, means definitely there the work will be what? 0. Okay. So this is what we have as the features of the work done, or the characteristics of the work done. Okay. Now since whenever we talk about any physical quantity, right, we always have to keep one thing in mind. We should look at what will be the units of that particular physical quantity and what is the dimensional formula. See, what will be the units? We are like in this case we have talked about the work done by the constant force, right? What is the formula for this? It is F into S into cos theta. Force, what is the SI unit? Newton or kg meter per second square. Into S is what? Displacement, right? Means it is meter. Cos theta is what? Trigonometric function that will not have any unit. Okay. So what is this? You see, kg meter square per second square. So this is named in honor of the scientist as Joule. So what is the SI unit of work? It is Joule. We will represent this by the symbol capital J. So what is this equal to? 1 joule means what is it? 1 kg meter square per secant square. Okay, and the dimensional formula, what will be the dimensional formula? Look at this, we'll take the same equation here. LHS will be the dimensional formula for the work. RHS is what? Force. Remember what is the force dimensional formula? MLT power minus 2 into displacement is what? Length, right? L. Trigonometry ratios will not have any dimensional formula. So look at this, what is it? ML square T power minus 2. The dimensional formula for the work will be what? ML square T power minus 2. Now we talked about the SI unit, but we also have one more common system, right? That is the CGS system. So we look at what is the CGS unit of the work. See, CGS unit means what? In place of Newton, we will get CGS unit of force, which is dyne. In place of meter, what we will get? Centimeter. So the CGS unit of the work is what? Dyne into centimeter, which is what we will call as erg. What is the CGS unit of work? Is it what? Dyne into centimeter. We will call it as what? Erg. Okay. And we are of course interested in knowing what is the conversion between the CGS unit and the SI unit. Okay. So look at this. If you have 1 Newton into meter. Okay, so we will not use the word Newton into meter. Why? Because this is Newton into meter, right? We will see when we go to the rotational motion chapter. Newton to meter will be taken as the representation of SI unit for another physical quantity called as torque. So generally when we talk about the work, right, we will not use the word Newton to meter. We will always use the word joule. Okay, but here since we are going to do the conversion, we are taking it. Okay, so look at this. What is 1 Newton? It will be 10 power 5 dyne, right? So 10 power 5 dyne. 1 meter will be what? 10 square centimeter. So what is this? Totally 10 power 7 erg. So 1 joule will be equal to what? 10 to the power of 7 erg. That is the conversion. 1 joule will be equal to what? 10 power 7 erg. So accordingly, if you want to do the otherwise, what is it? 1 erg will be equal to what? 10 power minus 7 joule. 1 erg will be equal to what? 10 power minus 7 joule. So this is important. Why? Because both the CGS unit of force and CGS unit of work, right, we'll see quite often. Okay, so these conversions we must be comfortable with. The conversion between the CGS unit of force to the SI unit, and the conversion between the CGS unit of work and the SI unit. Okay, clear? So this is about the units and the dimensional formula. Now what we'll do is we'll just look at some sample questions so that we'll be able to understand how we'll find the work in case of the constant force. So all this is what we're discussing, the idea to find the work because of a constant force. So look at this question. A block of ice is drawn through a distance of 500 centimeter along a smooth horizontal surface. The pull in the rope, so we are trying to pull the ice, block of ice by using a rope. The pull in the rope is what? 100 dyne, and the angle between the rope and the ground is 30. Find the work done. So look at this, what are we having here? So this is the ground or the surface. Okay, so the ice block is moving like this. What is the displacement here? We have to take 500 centimeters. This is along the horizontal surface. This is the displacement. Okay, now the rope tied to it. Okay, so the rope tied to it, the tension in the rope is basically the force. What is the force they are giving? 100 dyne. This is the force, but there is an angle between the two, right? What is the angle? 30. Okay, so here we can see the force is given in terms of the CGS unit, as well as the displacement is also given in terms of the CGS unit. Okay, now we have to find the work done, right? What is it? Straight formula. What is F into S into cos theta? What is the theta here? 30. So F is what? 100 dyne into S is what? 500 centimeter into what do we have? Cos 30. What is cos 30? It is root 3 by 2. So check it. What do we have? So this is maybe we can cancel 250s. Then what is it? 100 into 250, that is 25,000 into root 3. Dyne into centimeter is what? Erg. So if you want, we can further simplify it. We can take the value of root 3 as what? 1.732 and simplify. It depends upon the options. Okay. Sometimes, while they might give the force and displacement in terms of CGS unit, they might expect us to give the final answer in terms of joule. In that case, how do we convert this value, right? Whatever the work in erg, we have to multiply this with what? Into 10 power minus 7. That will give us what is the work in terms of joule. Because 1 erg is equal to what? 10 power minus 7 joule, right? So we'll have to simply multiply the work that is coming in erg with 10 power minus 7. We will get what is the work done in terms of joule. Okay, so here we are not further simplifying it, we are just leaving it as it is. So the work in this case is what? 25,000 into root 3 erg. If you want to convert this into the exact value, means we can use root 3 as what? 1.732 and then simplify it. If you are expected to give the answer in terms of joule, then what we'll do? We have to convert the work in erg into work in terms of joule. For that, what is the conversion factor? 10 power minus 7. Okay, is it clear, guys? So this is how we'll have this is very straightforward basic question. Next, look at this one. A force of 2I plus 3J newtons is acting on an object to cause the displacement of I plus 2J plus 3K in terms of meter. So force is in SI unit, displacement is also in terms of the SI units. Find the work done by this force. We need to find what is the work done by the force. So let us just look at what is given to us. Force is what? 2I plus 3J. Displacement is what? I plus 2J plus 3K. So work is given by what? Dot product, right? Between the force vector and the displacement vector. Remember, what is the dot product of two vectors? Here I component is what? 2. Here what is I component? 1. So product of the I components plus J component is 3, J component is 2. Product of the J components plus, here there is no K component, means 0, plus product of the K components. That is the dot product, right? For two vectors given to us, what is the dot product value? Product of the I components plus product of the J components plus product of the K components, isn't it? So this is anyway 0, which means what is it? This is a 2 plus 2 3s are 6. How much it is? 8. Unit is going to be what? Joule. Why? Because force is in terms of Newton and displacement is in terms of the meter. So both are in SI unit. So work will be coming in terms of joule. So this is another type of question where all we need to do is just take the dot product. See, when you have questions where we need to find the work done because of a constant force, right? They'll be pretty straightforward. And obviously in maybe at least JEE advanced level, we will never be able to expect questions on this particular area, because this is like very fundamental or the basic. But sometimes in JEE mains, right, we may get some questions like the questions will be not exactly related to the work, but they will be somehow related to the applications of the vectors. Like they can give us a question, there is this force and there is a displacement. They will give us both the vectors and they will say if the work done is 0 in the components, right? Like they may give force like this, force they will give it like this, okay, 2xi plus 6j plus 8k, like that they will give force, and they will give us the displacement. Then they will ask if the work done is 0, what is the value of x? So that is not exactly a question on the idea of work, but that is more of application of the vectors, because if you have work to be 0, the dot product should be coming as what? 0, right? And accordingly you will be able to find out whatever is the variable they are asking, you can find it out. Okay, so this is how we'll have questions on the work done by a constant force. Okay, so this is very basic thing. Now if we have many forces acting on that object, like say in Newton's laws of motion chapter also we talked about it. If there are many forces, like there is a body, there are many forces acting on it, F1, F2, F3, F4. So what will be the cumulative work done or total work done? Remember, so work is what? Work done by any force we are saying is what? F dot S. Means what? It is a dot product. What is the dot product? Dot product will be a scalar quantity, right? What is dot product? It is a scalar, which means if you are having a scalar quantity, we can simply add it up, right? Any scalar quantity, we can simply add it up. So for the force 1, if we say the work done is W1, what is this W1? F1 dot S. If S is the displacement of the body. What will be the work done by the force 2? It will be F2 dot S, because the displacement of the body will be only one displacement, right? What will be the work done by the force 3? It will be F3 dot S. What will be the work done by the force 4? It will be F4 dot S. So if somebody is asking what is the total work done, right, we will simply have to add all of them, that's it. Because work is a what? Scalar quantity, right? So scalar quantity, so we can simply add them like the way we add numbers. We can simply add all these works to get what is the cumulative work done or the total work done. Okay, so why we are able to do this simple addition? Because work is a scalar quantity. So remember, when we talked about the cumulative force, net force acting on a body means, if you want to find the net force, right, how do you find the net force? We will have to add all the forces vectorially. We have to add all the forces vectorially. That is what is going to give us the cumulative force or the net force. Correct. Now here look at this. If you want to look at what is the total work done, what are we saying? Simply add all the work values, right? Means what? F1 dot S plus F2 dot S plus F3 dot S plus F4 dot S. Remember, the dot product, it will obey the distributive law. So we can just take the dot S common and we'll write as what? F1 plus F2 plus F3 plus F4 whole dot S. So the cumulative work done is given by what? F1 plus F2 plus F3 plus F4 whole dot S. But what is this F1 plus F2 plus, this is the F net, right? So cumulative work can also be calculated by using the net force value. Cumulative work can also be calculated by using what? Net force. So net force dot displacement vector, that will give us the cumulative work. Otherwise, we can also just calculate work done by each of the forces, W1, W2, W3, W4, add all of them. That way also we can get what is the cumulative work. Both ways we will be able to get what is the cumulative work value. Okay, so this is about the cumulative work done when there are many forces acting on the body. Now when we talk about the displacement is going to be depending upon who is the observer, because we talked about the concept of relative motion in kinematics, and just in Newton's laws of motion chapter we talked about the frame of reference. Frame of reference means what? The observer. The question is, will the work depend upon the frame of reference? Think about it. Will the work depend upon the frame of reference? So we'll just take a very simple example. Let us say we have a moving object. Okay, so we have a moving object. On that we keep a block. So let's say the block is also moving. So whatever is the acceleration of the moving object, block is also having the same acceleration, means it is going along with the moving object. The block is going along with the moving object. Now if the moving object is having a displacement of some x, then moving object will go here. The block also will get the same displacement x. The block also will have the same displacement. Now think about it. If we have an observer who is standing on the ground outside, so he is the observer, what he will see as the displacement of the block? because he will observe that, okay, so block is initially here and finally block is over there. So he will see that the displacement of the block is equal to x. He will see that the displacement of the block is what, x. But look at another observer. Right? I'm going to take an observer who is also sitting on that moving object. That observer is also sitting on the moving object. Now think about it. If you are choosing this person as the observer, okay, now see what happens. He will be having some gap between him and the block initially. Now our journey is complete when the moving object is reaching here. So this is the initial position, this is the final position. The observer is still here only, right? Means he would see that the block with respect to him, because he is the observer, with respect to him, the block is not having a displacement. So with respect to the second, let's call them as what? Observer 2. The first person we took is what? Observer 1. Okay. So with respect to observer 1, we have a displacement for the block. But what about with respect to observer 2? Observer 2 is not seeing a displacement, right? Because for him, the block appears to be at rest. Because we're talking about the relative motion, right? So the work will depend upon what is the frame of reference. Just like, the displacement, the parameters of motion, they depend upon the observer, right? So when you say displacement, it is always dependent upon the observer. When we say velocity, depends on the observer. When we say acceleration, depends on the observer. So the work, just like the parameters of motion, is also going to depend upon the observer, because here work will be related to what? Displacement, right? Since displacement depends upon the observer, work also will depend upon who is the observer. Okay, so this is a very important theoretical concept. So if at all we are getting some theoretical questions on this work, energy and power topic, right, we may expect questions like this. So what we'll do is we'll just go through one sample question. Look at this one. A block mass 2 kg is lying on a flat car which is accelerating with a constant acceleration of 1 meter per second square. Means what? Look at this. We have a flat car. Okay, so we have a flat car. The 2 kg block is lying. Means we have to take that the block, right, is at rest with respect to the car. It's lying on the flat car means what? So we consider that the block is at rest with respect to the flat car. So what is the acceleration of the flat car here? 1 meter per second square. So we'll take that the 2 kg is also having an acceleration of 1 meter per second square. That's when the block will be lying on the flat car just like that. Okay. Now find the work done by the friction on the block in 10 meter journey of the car. Means the car journey is what? 10 meter. The car is moving forward by how much? 10 meter. In this 10 meter journey of the car, we need to find what is the work done by the frictional force. We have to find what is the work done by the frictional force. Here they are giving us two cases. Look at this. First they are asking what is the work done with respect to driver of the car. Second they are asking what is the work done with respect to ground observer. So look at this, we have the car here, right? So this is the car initial. Okay, so the block is here, 2 kg block. Car is moving with an acceleration of 1 meter per second square. Okay, so what is the journey of the car? It is 10 meters. Means if you are having an observer who is on the ground, so first we'll do B part. If you are having an observer who is on the ground, think about it. For him, the displacement of the 2 kg block will be what? It will be same 10 meters in the direction of the motion. Displacement is what? It will be 10 meters in the direction of motion. Now here we need to find work done by the frictional force. See, already we have seen these kind of cases in the laws of motion chapter, right? See, if we look at the free body diagram of the 2 kg block, the only horizontal force that is acting on this is the friction, because when the car below it is trying to move forward, right, then the frictional force acting on the car will be backward. The frictional force acting on the car will be backward, because frictional force has to follow the action reaction pair concept, right? So the reaction frictional force acting on the block will be forward direction. So the only horizontal force that will be acting on the 2 kg block in that is what? Friction. Because of the friction only, the block is getting an acceleration of what? 1 meter per second square, right? Here they have not given us the coefficient of friction, etc. Then we have to think how we can get this frictional force value, because that is the only force acting on that 2 kg block in the horizontal direction, because of which the block is having an acceleration of how much? 1 meter per second square. Means the frictional force must be what? Mass of the block, which is 2 kg, into its horizontal acceleration, which is what? 2 newtons. The frictional force acting on the 2 kg block must be what? 2 newtons, which will be in the forward direction, is the frictional force. Okay. Now for an observer who is on the ground, we are first solving the B part. For an observer who is on the ground, what will be the work done? He will see that there is a frictional force of 2 newtons in this case right side. What is the displacement? 10 meters to the right side. So what is the work formula? It's a constant force, right? Force into displacement into what is the angle between the two? They are in the same direction, means cos 0 will come. Cos 0 is 1. So 2 into 10 is what? It will be 20 joules. What is the work done with respect to the ground observer? It is what? 20 joules. Okay. Now we will look at the part A. What is part A? The work done with respect to the driver of the car. What is part A here? We have to look at what is the work done with respect to driver of the car. Okay, so when you look at this motion with respect to driver of the car, think about it. Okay, the driver of the car will see the block on the car. So driver is sitting here, imagine. He will see the block on the car at some distance from him. The final state also, he will see the same position of the block. Means what? With respect to the driver of the car, what is the displacement value? 0. Because the block is lying on the flat car, means we are assuming it is going with the same acceleration as the flat car. So for the driver of the car, right, he will not see the block is actually having a displacement. Since the displacement is 0, work also will be what? 0. So what will be the answer? Work in the first case, driver of the car will measure the work as 0, whereas the ground observer, right, he will measure the work as what? 20 joules. So you see here clearly the work, right, will depend upon what is the observer. Work will be depending upon who is the observer. That is what I am saying. The work is going to be depending upon the frame of reference. Work will be depending upon what is the frame of reference. Okay. Now all this we are discussing in the case of the constant force, but the force may be variable force. Variable means what? It may be changing in terms of the magnitude, or it may be changing in terms of the direction, or it may be changing in terms of both magnitude as well as direction. In that case, how are we going to find the work done? So let us see how we will find the work done in case of a variable force. Okay, so variable force means what? The force can change in terms of magnitude or direction or both. That is what we call as the variable force. Look at this. Here what we need to do is, because the force keeps changing, so for a small displacement ds, for a small displacement in the journey, right, somewhere we will take a very small displacement. we will look at what is that small work done. So the symbol D represents what? Already we have used this quite often. What is this? Differential element, very small value. For a small displacement ds, we will look at what is the work done. So what will be the work done? F dot ds, we can also write it like what? F into ds into cos theta. What is it? F dot ds or F into ds into cos theta. Okay, now we want to find the overall work done, means we need to integrate it. We need to integrate this F dot ds term or F into ds into cos theta term between the limits. See, for example, our journey is starting from A and ending at B. Integration has to be from the initial limit to the final limit. Integration has to be from the initial limit to the final limit. If you do this, then we will be able to find what is the work done. So here, to find the work done due to the variable force, right, we must use the integration approach. There are actually two methods. One is the integration approach, and second will be the graphical approach. So here this formula will tell us how do we find the work done because of a variable force using the integration approach. Later we'll see how we'll find the work done using the graphical approach. But the thing is, to find work done in graphical approach, we must be given the graph. We must be given the graph, then only we can find what is the work done using the graphical approach. Okay, but this is how we are going to find work done in case of the variable force. Okay, so look at this question. A force of 10 plus 0.5x, means we can write like what? 10 plus x by 2, like that we can write, acts on a particle in the x direction, where F is in Newton and x is in meter. Find the work done by this force during the displacement from x is equal to 0 to x is equal to 2 meter. Means here we have to consider that the force and even you take a very small displacement, right, both are in the same direction. So here we are considering that both the force and the displacement are in the same direction. Okay, so look at this. What is the force function? Force is given as what? 10 plus x by 2. Now here x represents what? The position of the particle. X represents the position of the particle. So look at it. When the position is changing, change in position will be what? Dx. This will represent what is the small displacement value. So change in the position, it represents what? The differential displacement value. Since we are assuming that force and displacement in the same direction, what is this? Work will be what? Integral F ds cos theta, cos 0 will be 1. So F is what? 10 plus x by 2. In place of ds, what will represent dx? So this integration, right, we have to do it because what they are saying, find the work done by the force during the displacement from x is equal to 0 to x is equal to 2, means here the integration is with respect to variable x. X value has to vary from 0 to 2. The value of x must be changing from 0 to 2. Okay, so now if we are able to conclude the integration, we will be able to find what is the work done. That's it. If you are able to conclude the integration, we will be able to find what is the work done. Look at this. So already we have seen the simple integration and all that we have seen in our basic math videos, right? Check it. So we will split this integral 0 to 2 10 dx plus integral 0 to 2 x by 2 dx. This is what? 10 into 10 is a constant, comes out. Integral dx is what? X, limit 0 to 2. Here half will come out. Integral x dx. What is integral x dx? X square by 2, correct? So x square by 2 limits are what? 0 to 2. Now look at this, 10 into final limit is 2, initial limit is 0, plus half into x square by 2. Final limit is what? 2 square by 2. Initial limit is what? 0 square by 2. 0 square by 2 means 0 only. So look at this, what is it? 10 into 2, which is 20. Here what do we have? 2 square by 2 means it will be what? 2 only. Already there is a half. So we'll have 1. So if you consider that the F is given in Newton and X is in meter, means work will be coming in terms of what? Joule. So 20 plus 1 will be what? 21. So the variable force problems, right? It's all about how good you are in terms of the integration. If you are comfortable in terms of the integration, then these kind of questions you will be able to solve easily. So you will just have to make sure that the basics of integration we are thorough. Then we will be able to answer these kind of questions very easily. Okay. Is it clear, guys? So what are we doing here? We are taking a very small change in the position. That will be the small displacement value. And for that we look at what is the work done. Integrate it. Okay. Now if the force and the displacement, in this case the force and the displacement are happening in the same direction, but if the force and the displacement are not in the same direction, right, like even the small displacement is not in the same direction, then generally what we do is we will represent the work by using the component form. See, force we can write it as what? Fx into I cap plus Fy into j cap plus Fz into k cap. The force expressed in terms of the component form. Small displacement, right? See, when an object is changing from one position to another position, small change in displacement, it will come with what? Small change in the x coordinate of the particle, small change in the y coordinate, small change in the z coordinate. So that small displacement vector, right, will be given by what? The I component of the displacement, which is what? Dx. J component of the displacement, dy. K component of the displacement, dz. So this is how we'll represent the small displacement value in terms of the change of the x coordinate, change of the y coordinate, change of the z coordinate. Now we want to find the work done, means what? It is, remember what is the formula we said? Between the limits a to b, a is the initial point and b is the final point. What is it that we said? F dot ds, right? So we have to take f in the component form, dot ds. So look at this, integral a to b, it is what? Fx into dx. Dot product is what? Product of the I components plus product of the j components plus product of the k components. Now we can split this integration. It will be what? Integral a to b fx dx, fy dy, fz dz. So if the displacement is not in the direction of the force, right, then we'll use this approach. What is the approach? We'll express the force in the component form, and the differential displacement is written as what? Dx into I plus dy into j plus dz into k, because the small change in position will be accompanied by what? Small change in the x coordinate value, small change in the y coordinate value, small change in the z coordinate value. That is how ds will be written as what? Dx into I plus dy into j plus dz into k. Then the work done will be given by what? Simply dot product f dot ds. But to get the overall work done, we have to integrate it. Okay, so this is how we will calculate the work in case the variable force displacement is in a different direction than the force. Okay, now we said we can find out the work done in case of the variable force by using the graphical interpretation or graphical analysis. So for this, right, we must have, if say force and displacement are in the same direction, then imagine we have the force and position graph given. Change in position represents what? Displacement. Like in this case, if force is along the x-axis and we are looking at the x coordinate of the particle, because the displacement has to be only along the x direction. Okay, now look at this. If they are giving us a graph What is the work done that we have? Integral f dx, right, between the limits a to b. So for example, if these are the limits, this is a and this is b, what is this f dx? If you take a very small displacement, right, dx, think about it, take a small displacement dx, the corresponding force, what is this? F into dx means it is like the area of the small rectangle. What is this? It's the area of the small rectangle. When we integrate, it means what we are essentially doing, we are adding up all these rectangle areas, isn't it? Integration is addition only, right? We are adding up all these rectangle areas. When you add up all the rectangle areas, what are we getting actually? We are getting the total area below the graph. So this is nothing but what, in terms of graphical significance, what is it? It is the area between the force curve and the position or displacement axis. Okay, so why are we calling position or displacement? Because change in position will give us what? Displacement. So here we are looking at what? The force to be in the direction of the displacement. Here we are looking at the force to be in the direction of the displacement. But if the force is not along the direction of the displacement, then you know what we need to do? We have to look at three such graphs. One is x coordinate versus the x component of the force. Remember, this is what? This is like integral fx dx. Then we have to look at y component of the force along with the y position. The area will give us what? Integral fy dy. Then we need to look at what is the z component of the force along with the z coordinate. That area will give us what? Integral fz dz. Because remember, just only we have seen it, right? What is it? The overall work done in this case is what? Integral fx dx plus integral fy dy plus integral f dash dt, which means what? This area plus this area plus this area will give us what is the total work done. If we are having the force and the displacement to be in different directions, but generally when we have graphical questions, right, we will be having the first type. What is the first type? We'll have situations where the force and displacement will be in the same direction. Means from one graph only we will be required to find what is the work. They will not be giving us three graphs and then ask us to find the work. They will give us only one graph. Means the kind of question that we'll expect is what? The force and displacement will be in the same direction. That kind of questions only we'll be getting. Okay, so this is how we'll be able to calculate the work from the graph. Now the thing that we need to keep in mind is, from the graph also we can expect work to be coming as a negative. It is not like work will be always positive. When we will account the work as a negative from the graph, when we'll account work as negative from the graph, when the graph is going below the x-axis, when the curve is going below the x-axis, right, then we will account the particular work as what? Negative. So look at this in some other question, right? They are giving us the plot. So this is the force versus position graph. See, from A we are starting the journey and finally we are ending up at B. This is the point C. So from A to C, this area will be taken as what? Positive, that is above the x-axis. But when you are coming from C to B, that area is what? Below the x-axis. So this part of the work, right, it will be taken as what? Negative. Whatever the value that you will have, we have to take it as what? Negative. So this is like what? W1, this is like W2. Total work means what? We have to do W1 minus W2. That is the total work done. Because that above the x-axis, work we will take it as what? Positive. Below the x-axis, work we will take it as what? Negative. Okay, whatever the area we get, we will simply take minus of that area. That will be the work. Okay, so this is how we will have to look at the interpretation of the negative work in case of the graph. We'll just look at sample question on this. A force acting on a body varies with the distance x as shown here. So force is varying with respect to distance. The force is in newtons, x is in meter. Work done by the force in moving the body from x is equal to 0 to x is equal to 6. So from here we are moving up to x is equal to 6. It's a straight question. Here we don't even have the complication of the curve going below the axis. Here the curve is not going below x-axis, right? So which means we have positive work in this case. So we need to find what work done by the force in moving the object from x is equal to 0 to x is equal to 6. If you look at the force, this is the force curve, right? This is the force curve. We have to find what the area between the force curve and the x-axis. So what is it? This area. Now here you can see this area, right? We can divide it into two parts. How we can divide this in two parts? Look at this, already they are given us the markation here. So this is like one part. It's like what? Rectangle. What is the work in this case? Area is what? Rectangle. What is the base here? 0 to 3 means 3 meter. What is the height? 0 to 3 means 3 newtons. 3 newtons into 3 meter. What is it? 9 joule. Okay. So what will be in terms of the SI unit? Now look at the second part. Second part is like this triangle, right? Second part is what? It is the triangle. What is the work in this case? What is the height of the triangle? Same. 3 Newton. What is the base here? 3 to 6 means what is the base? 3 meter. What is the area of the triangle formula? Half into base into height. So how much it is? 3 3s are 9. 9 by 2 is what? 4.5 joules. Total work done means what? W1 plus W2, right? Which is what? 9 joule plus 4.5 joules. How much it is? 13.5 joules. Generally, you know, when we are getting questions on this graphical approach, right, we'll be having relatively easier questions only, because at the end of the day, right, what will be expected here? Will be expected to just, you know, find out the areas. So maybe if it's little bit complicated questions, we'll have complicated shapes, like we'll have some semicircular part, or you know, a circular arc. So the geometry of the curve, they can little bit make it complicated. Okay, but whenever the curve is going below the x-axis, we have to be careful. That particular area, when we are taking it as a work, means we should take it as what? Negative value. When we take it as a work, means we should take it as what? Negative. Okay, so this is about the graphical interpretation or the graphical approach to find work done by a variable force. Okay, so with this we have understood how do we find the work because of a constant force, and how do we find the work due to a variable force. In the next session, right, we will start with the classification of the forces. As I said, you know, here already we talked about the types of forces before in Newton's laws of motion chapter. There, when we say types of forces, we were looking at what is the source. Like if the force is coming because of the gravitational pull of the earth, we call the force as what? Gravitational force. If the force is because of the the attraction between the particles in the rope, then we'll call the force as what? The tension force. If the force is because of the elasticity of the spring, we call it as what? Spring force. Like, you know, we were classifying the forces based on the source, like friction, etc. What is the source from where the force is coming? But now, right, we are going to classify the forces into two types based upon the way the forces do the work, and we'll see it in the next class. We'll call the forces as either the conservative forces or the non-conservative forces, and this classification is going to be based upon what? It will be based upon the work done by the respective forces. So depending upon how the forces do the work, we'll classify them either as the conservative forces or as the non-conservative forces. Okay. We'll see you next class.